Well, welcome back, guys. It's been a long week. Okay, quick look at our calendar. We know that where we're at. Today is the 12th. Lab 6 is due today, 2D7 due tomorrow, and along with the homework. Next week we have spring break, obviously. So we take a week off. And it's hard to imagine. It's been a year now since we had to convert through this online. Okay, so I won't be here this next week. So if you got an email, it may take a little bit of time for me to get to it. So I will definitely, I'm back on the 20th and catch up on my stuff for that weekend. So then the following week, when we get back, the week of the 22nd, we have exam number 3, which covers chapter 7 through 9. Today we'll be doing chapters 8 through 9. Knock those out and get ready for the exam. So, any questions about that as far as what's coming up? Yeah. All right. Well, let me jump right in there and proceed with chapter 8, which deals with nomenclature. Okay. Nomenclature is nothing more than naming compounds. Now, what we're going to be doing is not only we're going to learn to name them, I have been doing that as we've gone through the chapters, bring up the name of these compounds that we make, but we're also going to be, we also start working on putting formulas together. And so when this chapter, it ends up being either you're given the formula, you give the name, or you're given the name, give the formula, back and forth. Remember that I did have, let me see, make sure I'm showing that up here. And I've stated this before, but I'm going to put just to make sure everyone understands and knows about it. There is on the course website a study mate. I'm showing that on the screen right now on the far left side, not all the way to the left, but the second column of links. Click the study mate. Okay. You should have a nomenclature practice. There's 143 compounds have been uploaded with the name and the formula. So if I click on the nomenclature practice for you, this pops up. I find that the flashcards and the matching works the best. The other ones, you can try them out. Some work okay because this particular study mate doesn't understand parentheses. Sometimes you need parentheses. So in the crossword puzzles, you need parentheses and it doesn't offer that option. So, but you try it out, see if you like it. The flashcards are straightforward. There's 143 compounds. For example, you got chromium number 6 carbide. And what is being asked is, what is the formula? So you flip it around. You're working with chromium plus 6, and carbide has a negative 4, so you need to come up with a combination here of the formula here. Excuse me, I had a senior moment for a second. Chromium and then carbide 2, subscript 2, and then a 3. 10 for carbide, etc., so on and so forth. Okay, so that helps you out. If you don't like the flashcards, you can use the matching. Matching works great. Here's one, carbon disulfide, to give you the name. You're looking for the compound, and so you go around, figure out, okay, which one do I need? So carbon and disulfide, and it gives you the correct. All right, go to the next one. Lead peroxide. If you click the wrong one, you get that answer. No, it's incorrect. So that's a study, 143 compounds for your use, which is related again to the nomenclature exam, which I stated. I sent an email about that. Everybody has a 0 in there right now to give an idea what your score truly is. You have an unlimited number of attempts. Departmental requirements is that you get at least an 80% minimum to get a passing grade. The 80 stays on. Anything less than 80, it's a 0. So it can affect your grade if you're on the border. So don't forget about that. Okay, we're halfway done with the semester. I don't think anyone's tried it yet. So start, even though you don't know the names right now of everything, just practice. That's another way to practice. Keep trying that exam until you're at the score that you need an 80. There's 20 questions, so you need 80% of that for passing. And once you're done with it. Just leave it alone. Okay, nomenclature. All right. With respect to the right now, we're going to start with ionic compounds. That's a combination of metal and non-metal compounds. Okay. So, and I've stated this before with respect to the metals, there's really no name change. We just call it's a sodium atom or a sodium ion if we were talking about the ionic metal. Okay. So we mentioned this also before. Be familiar with at least the first 20 elements and their symbols, and include on that. There's a short list. We will be adding more as we progress. Ba is for barium, Co is for cobalt, I is iodine, Cu is copper, Fe is iron, Pb is lead, Hg is mercury, Ag is silver, Au is gold. Those two get mixed up quite a bit, Ag and Au. Au, it comes from orium, the Latin term. And then Zn for zinc, Sn for stannous, or you can use the word tin, Tin. So next time you get your toothpaste container, read the label. You see you're probably brushing your teeth with stannous fluoride. You're brushing your teeth with Tin. Strontium, nickel, Ni, bromine, Cr for chromine, manganese for Mn, and Cd for cadmium. Okay. Now, the other aspect about the elements, I'm going to share the periodic table, is this, because the charge is going to be very important. Charge / oxidation number. We've been talking about the charge of the ion, plus, or negative. We'll be switching the naming of that to oxidation number. Okay, because when we get to covalent compounds, we're not really talking about charges. We're talking about an oxidation number. And so to apply it throughout ionic or covalent, we'll start using the term oxidation number. Okay. But there are 16 metals that 100% of the time, their oxidation number. They are constant. They don't vary. They don't change. Okay. Now the metals in group 1, excluding hydrogen. Hydrogen is not a metal, but the metal starting with lithium in group 1A down. Okay. There's 6 right there. 1, 2, 3, 4, 5, 6. That's the first 6. They always, as we know, will have a +1 charge when they +1 oxidation number when they become an ion, because they all have 1 valence electron and they're all metals and they all lose electrons more readily than non-metals. Okay, so they end up with a +1 oxidation number. Group 2A, starting with beryllium all the way down. 2 valence electrons, all metals, will end up with a +2 oxidation number. So there we got 12. Constant the whole time. Now, we need to know this because we're going to talk about naming the other ones that vary, and we use a different technique, process, or procedure for that. Now, the other 4 I've highlighted in a circle. Aluminum, number 13, element 13. It's a metal. It's in group 3. We'll have a oxidation number always of a +3. Now, if you go caddy at an angle, let me draw it this way. From aluminum down in that direction, the next one, caddy corner or diagonally, is zinc. Always has an oxidation number of +2. And then Ag, silver, always a +1. From silver, we go to the right, make a right turn, if you will, and we go to Cd, cadmium. Always has a +2. So those are the 16 elements on the sweet 16. 16 metal elements that you have 100% of the time know their oxidation number, and they don't vary. That implies that all the other metals will vary with respect to oxidation numbers. For example, written in blue there, copper, there are 2 states of copper oxidation numbers. Well, actually 3, because the one all the elements have in common is 0 when they're all an element, right? But they can lose 2 electrons and therefore having a +2 oxidation number, or they can lose 1 electron having a +1 oxidation number. Now, to distinguish the two, the old way of naming these, we used to use a cupric and a cuprous, which is fairly ambiguous. So that was kind of been taken away. We don't want to deal with that. We use Roman numerals. And so for copper 1, we would write copper, and then in parentheses, write the Roman numeral 1, okay? And copper 2 will be copper, parentheses, Roman numeral 2, and parentheses, but more on that in a bit, okay? Now, the anions, the single nonmetals, the ones that we deal with a lot with respect to Chem 130 are this right here, nitrogen and phosphorus. Okay. They are nonmetals. They gain electrons. They're in group 5. They end up with the -3 charge. Okay. Not only that, the name changes when these guys become ions. So nitrogen's name becomes nitride. Phosphorus becomes phosphide. Okay. The other 2 that we do quite a bit of work with is oxygen and sulfur. Not to say we don't use the other ones, selenium and beryllium. Yeah, the same procedure if we need to use it. But oxygen becomes a -2 oxidation number. So the sulfur -2, because they both gain 2 electrons to get that magical 8, because they're both in group 6. Their name changes from oxygen to oxide. Sulfur becomes sulfide. Okay, so you can see that the nonmetals, when they become ions, their name changes. The metals, when they become ions, the name does not change. And then the other set that we use quite a bit is the fluorine, the chlorine, the bromine, the iodine. Okay, fluorine, chlorine, bromine, iodine, when they are the elements. They are in group 7. Okay, they're nonmetals. They will gain 1 electron to get that magical 8 of 8 octet. Therefore, they end up with, all of them end up with a -1 charge. So, and the name changes. So fluorine becomes fluoride, chlorine, chloride, bromine becomes bromide, iodine becomes iodide. Okay. Now, not to be confused, for example, down here, let's go to group 2 nitrogen, for example. We have down here nitrate and the polyatomic ions. Remember those? Okay. So we have nitrate and nitrite. Now, those are the given names for those polyatomic ions. That name does not change. We don't do anything change to the name at all. It is nitrate, it is nitrite. What happens is, because you can see nitrogen, we just talked about it. Let me see if I can do this here. Nitrogen becomes a negative 3 ion, and the name becomes nitride. Okay. So the name nitride, the IDE, should tell you I'm dealing with the single element. The moment we start adding ate, ATE, and ite, ITE, okay, that's a flag for you to say, okay, I still got nitrogen because of the NIT, but the ATE tells me I'm dealing with oxygen bonded to that nitrogen. I'm dealing with polyatomic ions, okay? And all of the anions, the IDE ending tells you I'm dealing with the single element. The IDE is a single element. Again, I start sticking in the ATE and the ITE. We're dealing with that element, but with oxygens and creating polyatomic ions. Okay, so 100% of the time, those are the sweet 16. We know those oxidation numbers 100% of the time, which is good because we can utilize that to calculate the oxidation number of its partner if we don't know what it is, because if we don't know the oxidation number of the partner, what we do know is the following: that the number of cations, plus the number of anions will equal the charge of the molecule. So here's our very generic algebraic equation to determine the charge of the cation or the anion, because most of the time we're going to be dealing with the charge of the molecule will be equal to 0. Okay. And so what we don't know will be one of either the anion or the cation. So we can solve for the partner's oxidation number. Okay. So total number of cations plus total number of anions equal the charge of the molecule. This equation will work for any multiple of compounds, either neutral compounds or if you're dealing with polyatomic ion compounds, because the charge of the molecule is its charge, a -1 or a -2. You plug that in there. Okay, so this equation fits for literally all scenarios. And we'll do some examples in there here in a bit. Okay, so ionic compounds, as I stated, we're dealing with metals and nonmetals. And of course, if you don't know by now, hopefully you do, covalent compounds, we're dealing with nonmetals only, okay? We also call those molecular compounds. Now we have the monatomic ions, the sodium, the chloride, the calcium, literally any of the elements that have been are now ions, either by gaining or losing electrons. Those are the monatomic ions. And then, of course, we have the polyatomic ions. These are these groups, a packet that we keep together. Those are in that table of the periodic table. First one's a sulfate with its corresponding -3. The OH, which is the hydroxide, the CO3 -2, is the carbonate. So you can see in that general equation I gave you, if you're trying to figure out the oxidation number of carbon while it is incorporated as a carbonate, we can calculate it using that equation because we know that the oxygen will always have a -2 and there's 6 of them. So we can set that up to say carbon -6 is equal to -2 in carbon. Okay, oxidation name, fancy oxidation states, fancy name for the charge. Okay, we all know again, all elements have a 0 charge. Why? Because they have an equal number of protons and electrons. Okay, equal number of protons and electrons. Protons are positive, electrons are negative. So if I have 10 positives and 10 negatives, zero, net zero. Okay, so we talked about the fixed charge. There's 16 of them. Add in here the silver and the zinc. And then all the other elements have a variable charge. Okay, variable charge. We all know again, hopefully by now, that metals lose electrons to become cations. And they become positive. Losing losing negativity, being the negative of the electron, makes you more positive. Okay. So I just mentioned here group 1 valence electron, always a +1. Group 2, always a +2. Group 3, always a +3 for the metals. Okay. The one above aluminum, boron, being a metalloid, it can vary. It depends on the conditions, but by and large, it loses also the three electrons. Zinc and cadmium always have a +2, so we're always a +1. All the other metals, their oxidation number can vary from a +1 to +9. Very, very wide range. Okay. And so to describe those, to be able to determine which one we're talking about, we use the Roman numeral. For example, copper +2. Okay. Copper is not part of the 16. So we have to use Roman numerals. So the fact that it says +2 says if I need to write the name out, I will write it out as copper, parentheses, Roman numeral 2, and parentheses. Okay. So that Roman numeral pertains to the oxidation number of the metal only, has nothing to do with the group number on the periodic table. Okay. I emphasize that one more time. The Roman numeral on these metals that we see here in the name represent the oxidation number of the metal that you're working. It has nothing to do with the group number on the periodic table. Okay. Iron 3, there are two types. There's an iron 2 and an iron 3. Here, they're demonstrating iron 3 +3. I should be specific, iron 3 could be -3 or +3. So iron +3, and as iron, Roman numeral parentheses, Roman numeral 3. Okay. And then there's lead +4 to designate that in writing with respect to its name. It will be listed as lead, parentheses, IV, Roman numeral IV, and parentheses. By convention, the Roman numerals are uppercase. I know you can write lowercase Roman numerals, but by convention, uppercase Roman numerals. Okay, the anions, I showed you the periodic table. Okay, group 5, always a -3 because they're nonmetals, they're gaining electrons. Group 6, always a -2. Group 7, always a -1. Now, fluorine will always, 100% of the time, will always have a -1. The other ones, chlorine, bromine, iodine, they had the capability of not having a -1 all the time, especially when the other ions or the halogens like chlorine, bromine, iodine, they can act as a central atom. Okay. Therefore, the oxidation number changes. And of course, Roman numeral 8, we have the octet. So all the noble gases have an oxidation number of 0. Okay. Because of the magical 8, if you will, that 8 electrons, valence electrons, with the exception of helium, which is as you know, A +2. All right. Now, metal and non-metal combinations. We're going to begin learning formulas and names for these ionic compounds. Remember that with respect to ionic compounds, are made up of ions, and ions have a charge. Okay. And the sum of the charges must equal 0. Hence that equation, total number of cations plus the number of anions equals the charge of the compound, which here would be 0. Okay. The polyatomic ions, you got that? Remember those? Okay. These are the in the table are the most common ones that we utilize. And the thing to remember here is that they're kept as a group. So if I need 2 nitrates, 2 NO3s, I would put a parenthesis around the NO3 and put a subscript 2. Okay. I would not change the nitrogen to a 2 subscript 2 and the oxygen to a subscript 6. What do I mean by what do I mean? Well, let me give you specifics. All right. If I need to use more than 1 nitrate, then I put them the whole unit in parentheses, and X can represent a number 2 plus a number 2 and above. If you just need 1, you don't need no parentheses. But if we needed 2, for example, to be specific, let me say we needed 2. Okay, we would just put the 2 outside the parentheses. We would not change the polyatomic ion in that manner, because this is, I have no idea what this compound is. So you put a parenthesis around it if you need more than 1. If you only need 1, you don't need a parenthesis. Okay, compounds must be neutral, enough cations and ions equal 0. So the question is, let's combine sodium and nitrogen. Okay, so what they do is they give you the element. So from the element, you need to convert that into ions. So that's where we know that sodium is in group 1, so it will have a +1 charge. And nitrogen is in group 5, and so it would have a -3 charge when they are in ionic form. We also got to remember that when we combine them together, we have to add enough cations and enough anions so they cancel each other out. Nitrite has a -3. No, sodium has a +2. So that tells me that I'm going to need 3 nitrogens. So that 3 I wrote, kind of crazy looking 3. That 3 I wrote in front of sodium ion will become the subscript for the formula. And that is my formula. Na3, subscript 3, nitrogen. Or in this case, nitrite. The name would be sodium nitrite. Okay. Sodium nitrite. And, like I said, you could be given the name or the formula, and you need to get either one to the other. Given the name sodium nitrite, what is the formula? Given the formula Na3N, what is the name? Okay, let's do some more. Okay, here we have another one. Similar situation. We got sodium. Okay, so you're given the elements. First thing to do, take a systematic approach to it, and then eventually you get comfortable and you go right to the formula. But until such time, break it down. Okay, to the ions. So we got sodium, which is a +1, and we have sulfur, which we know is in group 6. Well, it becomes a -2. And guess what? Its name now changes to sodium sulfide. Here, let me just do it this way. So we'll come back to the names Okay. Because I need 2 sodiums because they're +1. Each one's +1, and I need 2 of them. Right there. All right, next one. Magnesium. Okay, so break it down to the ions first. Magnesium is a group 2. It's a +2. Oxygen also is in group 6, so it will become a -2. Okay, both of these are a +1 and a -2, so I can put them together in a 1-to-1 ratio. So my formula becomes MgO. That's it. Okay, here we go. Same thing. You got the elements. We want to figure out the ions first. We know potassium's in group 1. It will be a +1 charge. And phosphorus is in group 5, so it will have a -3. Okay, that tells me that I need 3 K ions, potassium ions, for every phosphide. So our formula becomes A3PO. Okay, this one's a little more challenging here. I'm going to get some interaction here from you guys. All right, calcium. What do we know about calcium? It will be a +2, correct? Nitrogen becomes nitride with a -3. All right, now in the previous examples, I couldn't put them together as a 1-to-3, a 1-to-2, or even a 1-to-1. What do I have here? I got a calcium, which is a +2, and a nitride was a -3. How can I put them together? Okay, Cl3N2. That's correct, Thomas. We need to find a common number here. Now, there's a couple ways to do this. Just like if you were trying to add the fractions 1/5 and 1 + 1/7. You could have added them directly. So I got to find a common factor, and 1/5, 1/7, common factor would what? Maybe 35. So I convert to the 1/5 to 35ths and the 1/7 to 35ths and add the thing. Here, our common number is 6. Okay. So I need 3 calcium ions and 2 nitrites, because with the 6, I end up with a total of a +6 charge for the calcium and a total of a -6 charge oxidation number for the nitrites. And so that 3 in front of the calcium becomes the subscript. So we got calcium 3 nitrite. Okay. Now I think if you think about it, let me clear my. You can notice that the sure that's the right one. Notice that the 2 on the nitride was the oxidation number of the calcium, and the 3 on the calcium was the oxidation number of the nitride. So that itself could assist you to figure out what will be my subscripts. Okay. All right, next one. We have aluminum and the chlorine. Ions, aluminum always has a +3. It's in group 3, and the chlorine becomes chloride. Okay. That means I need 3 chlorides per 1 aluminum ion. And so our formula becomes AlCl3. Zinc is a +2, and I will continue again, break it down first into the ions. Zinc always has a +2. I always put a circle around my charge so I know that's the charge and not anything, not a subscript or anything like that. With the circle around it, there's no question to me that is a charge or the oxidation number. So I got a -1 on the iodides. Zinc is a +2. That means I need 2 iodides. Okay. So our formula becomes ZnI2. Okay, now we got the copper. Cu Roman numeral 2. That tells you that you are utilizing copper 2 +2. Okay. And oxygen is in group 6. And so it will always have a -2. Okay. So we got copper with a +2 and oxide with a -2. So I can very simply put them together. Okay, here we have another one with a variable oxidation number, and that would be lead. Roman numeral IV, which is +4. We know the oxides are a -2. I need 2 of them to cancel the +4 of the lead, 2 oxides. And so our formula becomes PbO subscript 2. Okay, so with that, let's go back and name them. All right, so the first one, sodium. Okay, sodium, we don't change the name of the metal. Notice also the trend here when writing these formulas. The metal always goes first, okay, in this combination with ionic compounds. Metal written first, which it also infers that that is also the central atom, that everything else is bonded around the central atom. So sulfur, we wouldn't call this sulfur because now it's ionic sulfur. So its name now is sulfide. Okay. Magnesium, oxygen, became ionic. It now is oxide. That's it. All right. Potassium. Phosphorus, the name phosphorus becomes ionic, becomes phosphide. Okay. Anybody want to take a shot at Ca3N2? Okay, Ca is calcium. No change there. What about the nitrogen? Nitrogen is the element. It becomes, what do we got here? Not nitrite. Okay, nitrite would infer the oxygen. Okay, if you look at your polyatomic table, you'll see the 8 ATE and the ITE. Here it's just nitrogen all by itself. So it would be the IDE, NITRIDE. Notice that suffix IDE. Notice the IDE in all of them. The sulfide IDE, oxide IDE, phosphide IDE, nitrite IDE. Okay, that's to tell you that you're dealing with ending in TE would be oxygen. That is correct. ITE. And so the IDE just tells you you only have the element itself. That's it in ionic form. When you throw in the ATE, let's take a look at this. Nitrogen, nitride had a -3. Nitride. okay, NO subscript 3 superscript -1 nitrate, NO2 charge the polyatomic ion, NITRITE. Oh, sorry. Okay. Look at the trainer. Let me see if I line up the naming. The IDE, the NIT tells you nitrogen. Okay. And you can do the same thing with the sulfate, the sulfide, when you have sulfate and sulfite. The sulfide is a single sulfur. Here, the nitride is a single nitrogen. NIT is a nitrogen. The nitrate, the NIT still deals with nitrogen, but the ATE ending tells you I got oxygen, and ATE specifically, 3 of them. And then the nitrite, it's still nitrogen, but the ITE tells you we got oxygen here, specifically 2 of them. And you can go through the same scenario with the sulfide and the sulfate and the sulfite. Okay. Which is a good thing to know because sometimes you're given a name, sodium nitrate, write the formula. When you see nitrate, boom, that sends you to the polyatomic ion table. Okay, if it says nitride, dealing with single nitrogen. All right, in this one here, we have aluminum. And then chloride. Okay. Then we got zinc, iodide. Okay. What about now? Notice again. Look at all the anion, the negative charge, the negative anions. Okay, all of them have the IDE. So that's the single element itself, the single non-metal by itself. All right, what about this one? I got CuO. I need to write the name of that. How would I present that? Okay, I need to write the name for CuO. We know that's copper. And we were given Roman numeral 2, so we continue to use it because that's designating to you that you are using the +2 copper. And then oxygen remains oxide. Now, keep in mind here that we are working with ionic compounds, and the anion, yeah, oxide, you got it. The anions, hold on a second. The anions, the negative charge ions of sulfide, oxide, phosphide, nitride, chloride, iodide, oxide. Okay, when we move over to covalent compounds, that naming of those elements in that form continue. Okay, so carbon dioxide. Carbon dioxide is a covalent compound, but we continue naming it oxide. Okay, so the name stays whether it's an ionic compound or covalent compound. And then finally here we got lead. Roman numeral 4 oxide. Okay, and so the point of that, the naming here is to tell you that be prepared to go both directions. That given the formula, give the name, or vice versa, etc., etc. Not only that, you can mix and match. What do I mean by that? You know, we've just been working with specific combinations here, but you can take that sodium, combine it with oxide, take the sodium, combine it with a phosphide, sodium with the nitride, sodium obviously with the chloride, sodium with the iodide, and we did the oxide already. You can do the same with the magnesium with the sulfide, magnesium with a phosphide, magnesium with the nitride, magnesium with the chloride, etc., okay? And so you have, I don't know, a couple hundred combinations here. And we just added, we had those 20 metals, or the 20 elements, and some more metals, but you can do this with all the metals, any combination thereof. Okay, so you're probably up to about 500-600 compound names by mixing and matching, right? In fact, the 143 that I uploaded, if I were to separate them, and maybe someday I'll write a program for it, but you have about 20,000 combinations, compounds, with just 140 that were uploaded. But they're not 20,000 combinations set up right now. I didn't break them up into the cations and anions. That'll be a good project for somebody who wants to learn how to write programs and such. Anyway, let's continue. All right, so every time you put a metal and non-metal with respect to these examples we've done, make sure that you have sufficient of cations and anions equal to 0, okay? Now, for the polyatomic ions, the names are, like I stated, are what they are. We don't change the name. So we look at this, we got magnesium, okay? And let me go through this systematically again. We do a step approach of this. We got magnesium, break it down to the ions. We know that magnesium is in group 2, so it has a +2 charge. The hydroxide given to you has a -1 charge. That is a polyatomic ion. So that means that I'm going to need 2 of these guys, 2 hydroxides, to cancel the +2 of the magnesium ion, which then tells me that I'm going to need a parentheses around the hydroxide and the subscript. And then the subscript 2 are outside the parentheses. So its formula becomes as follows, okay? And its name would be, we'll come back to the name, but it's magnesium hydroxide. Although AKA milk of magnesia, by the way, okay? All right, we have potassium and then the PO4 -3. That right there should direct you to the polyatomic ion, because you may not remember, it's not phosphide, but it's phosphorus, is oxygens attached to it. So that should send you to the polyatomic table, and you will find that that is called the phosphate. We know that potassium is a +1 charge, and we're given that the phosphate is a -3 charge. Okay, so that means I'm going to need 3 potassium ions to cancel the -3 of phosphate. And our formula becomes K3PO4. Notice that a parentheses was not necessary around the polyatomic ion PO4 because you only needed 1. Okay, you only needed 1. So you just, that's all you got to do. Put PO4. Next one. Same analysis. We have a SO4 -2, 2 negative, -2. It's the same thing. All right. That should send you to the polyatomic ion table to get a name, But here we just need to write a formula. And we know that silver always has a +1. And then we're given the sulfate there with a -2 charge on it. That tells me I need two positive silvers per sulfate. And so our formula becomes Ag2SO4. Again, I only needed one sulfate, so no parentheses. Okay, here we have the calcium atom. We need to break it down to ions first so we can know what we're working with, what we're dealing with. And we got the calcium is a +2. It's in a group 2 metal. We lose 2 electrons. The NO3 -1 is the nitrate. I need 2 of them to cancel out the +2 of the calcium ion. That tells me that I'm going to need a parentheses around the NO3. Okay, because I need more than one. So our formula becomes as follows. Okay. Same setup. Copper 2, as we discussed, has the Roman numeral 2 represents a +2 of copper. Then there's another polyatomic ion here with a -2. All right. So it's a straightforward 1-to-1, one copper ion and one carbonate. So its formula is a real straightforward 1-to-1. CuCO3. Okay. So the point here to remember, when you need more than one polyatomic ion, that is, you use the parentheses. Now, with respect to naming, let's name them. Who would like to take the first one? What do you think the first one is? What is the name of Mg parentheses OH and parentheses? Anybody want to take a shot? What would be the name of Mg? How about magnesium? Okay. Okay. All right. What and the hydroxide exactly, Alexandra? And the OH is hydroxide. If you don't remember, keep in mind you're given OH minus, okay? That should flag you to go to the polyatomic ion table. And it's not a hydroxide, it's hydroxide. The same thing, hydroxide, the same, tomato. Okay, so yes, it's hydroxide. It's the same thing, AKA magnesium, milk of magnesia. It's a base, which we're going to be learning about pretty soon. All right, how about the second one here? We got K, which is potassium. What about the rest? What do we got here? Phosphate. Okay, Leah, you got it. We'll leave it at that. Phosphate. Okay. Who wants a shot at the next one? Ag2SO4. Ag, which will be silver sulfate. You got it, Christina? No, not sulfite. Okay. Sulfide, I should say, IDE, because that would imply the single sulfur. Okay, not here because we got oxygen right next to the sulfur. What about the next one? We like that one. Go for it. Yeah, calcium. I'll give you that part. nitrate, exactly. Okay. And finally, what about the CuCO3? What do you think? Copper 2 carbonate. Very good. That is correct. Notice we use, now if you put a space after the copper, that's not, or don't put a space, it makes no difference. I will give you credit for either one. We've been trying to teach, what I mean is right here, for example, a space after copper or not, no space. Either one's acceptable for me. I've been trying to teach Canvas to recognize that space. Canvas doesn't have that AI, it doesn't understand it, that is proper. But anyway, if you ever add a space in Canvas in one of your answers and you get it kind of wrong, please let me know and I will get it correct. Now, with respect to the names we just did, notice the only one that had a Roman numeral was the last one. All the other ones did not have Roman numerals, okay? Because all of the other metals were part of the 16. And being part of the 16, they have a constant oxidation number and it's understood. So you don't need to add the Roman numerals. In fact, it would be incorrect to say magnesium Roman numeral 2. Okay. The naming of compounds, and not just these, but everything, literally everything that's created in chemistry is governed by an international organization, and that's to make it possible for to get rid of ambiguity with respect to naming of the compounds. And so the rules are very strict. We follow by the rules there, so we can make sure that a scientist across the other side of the ocean understands what we're talking about. And this is really, chemistry is really a language of sorts, because I recall I was in the lab, we were discussing how to make a particular compound, and myself had a scientist from Japan and a scientist from Lebanon, and we have one more scientist from Egypt, China, excuse me. And so we all conversed in English. It was kind of broken up. You know, my Chinese Mandarin is not good, nor was my Japanese. And so what we did was just went to the board and start writing chemical reactions. And just simply by chemical reactions, everyone understood what was going on. We came up with a plan to make a compound. Anyway, so that's very, very specific. No Roman numerals for those 16. That means all the other metals require Roman numerals. And for the polyatomic ions, parentheses if you need more than one. All right. There's my stuff here. Okay, naming these. Now that we can write these, we got to learn to name them. Okay, so basically most of the stuff we already talked about. Nothing really new here. Fixed charge metals, we don't use Roman numerals like I stated. Now, we got the formula NaCl. We know that chlorine is not chlorine with respect to the name because it's in a compound, specifically an ionic compound. So therefore, the name goes from chlorine to chloride. Now, sometimes I've seen people mistake, and that's okay, it's an honest mistake. They see the formula of BaCl2 and they think, okay, this is barium, which that part's correct. But then they think that this is chlorine. That's Ne there, chlorine. Well, that part will be incorrect, right? because even though they see a 2 here, and it's thought it's diatomic, but it's not the case. Why? Because there's a metal written first, followed by 2 chlorines, or in this case, chlorides. All right. So if the metal was not there, then yeah, that's chlorine, diatomic element, chlorine. But we got a metal first, a compound, a element's written first. So I'm just going to put M for generic metal here. Okay. And then we have to change the name to chloride. Okay. All right. This one here, what do we got here? Well, what would we call KBr? Anybody want to pick the name on that? K would be potassium. Would that be potassium bromine? No, it would be potassium bromide because it is an ionic compound. Okay. Here we have magnesium, and then we have oxygen in ionic compound, which makes it oxide. So we have magnesium oxide. Then we got calcium. Now here's an example where you might think, oh, okay, we got fluorine, but we got the metal calcium first. So that tells you ionic. So we're not dealing with fluorine, we're dealing with fluoride. Okay. And we know there's 2 fluorines is correct because each fluoride, I should say, is a -1, and calcium is a +2. It's in group 2. Lithium sulfide. Here we go with the IDE again. It's a single element. IDEs, in this case, sulfur, so it becomes sulfide, not to be mistaken with sulfate and sulfite. And we got silver chloride. And, you know, the key thing here is notice that we didn't use prefixes. For example, we named it for calcium number 3 is simply calcium fluoride. It would be incorrect to say calcium difluoride. We're not working, when you're working with ionic compounds, there are no prefixes. Okay. And so number 4 would just be called lithium fluoride, not dilithium sulfide, excuse me. Okay. I think the only place you'll see dilithium will be in Star Trek, dilithium crystals, as far as I know. Now, some people use that. I don't know why, but it's incorrect. And I think a lot of it's marketing and so forth, because I see labels for material and I just gasp at the names they put in there. Anyway, no prefixes for ionic compounds. Okay. Yes, prefixes for covalent compounds. I repeat, ionic compounds, no prefixes. Covalent compounds, yes, prefixes. Hence, carbon dioxide, carbon monoxide, so on and so forth. We'll learn more on that here in a bit. Polyatomic ions, they are, the name is what it is on the polyatomic ion table. We don't change it. Now, the question is, how do I know? How can I recognize that I have a polyatomic ion? General guideline is this. First of all, you see potassium written first. You know it's an ionic compound because the metal's written first. We got K written first. Then what follows is the phosphorus, right? And you might think, okay, maybe I'm dealing with a phosphide, but there's a difference here because what's immediately following that phosphorus are oxygens. Okay, so that's a flag to say polyatomic ions. Specifically here is the phosphate, because if you see PO4, that sends you to the table. So you can look it up, until you become familiar with it, and you'll see, recognize that PO4 is a -3 polyatomic ion, which is consistent with 3 potassium, right? Because each potassium ion is a +1. All right, so you know for sure that that is the phosphate and not the phosphide. Okay, and so the name would be, where are we? Okay, now if this would have been written, no, where's my pen? If this would have been K3E, what would be the name of that? Better want to take a shot. Let me see if I can draw this a little better. Okay. I got potassium, 3 of them, and 1. What would be the name of that formula? It's a legitimate formula. Okay. Going through the same systematic approach you did earlier when I was going through the first one, I see potassium first, K. All right, so that tells me it's an ionic compound. No prefix is necessary here, right? Then I see phosphorus right there, all by itself. Okay. There's no oxygens after that phosphorus. So what must be the name? Potassium phosphide. Okay. Phosphide. Okay. And we got this one here. We got Ca, which is calcium. We got a parentheses. The parentheses is a good flag for you to go to the polyatomic ion table. Okay, because remember, when we need more than one polyatomic ion, we need parentheses. So then that sends me to go look for OH, which is the hydroxide polyatomic ion. And so the name here would be calcium hydroxide, which, by the way, if you eat a lot of Tums, this is one of the key ingredients, calcium hydroxide. Okay, all right. Here we have zinc, sulfur. Okay, and then immediately after sulfur, you have oxygens. So it's not sulfide, but it is either the sulfate or the sulfite. You go to the periodic table, you'll find that the SO4 is the sulfate. Okay? And so its name will be zinc sulfate. Now, let me put all of these other ones together. I should have done that with the phosphate, but I'll do it here. Okay, we have the zinc SO3 and the zinc S. Okay, so with respect to names, this would be zinc sulfite. And the next one down there would be zinc sulfide. Okay, So again, I could overemphasize that the IDE tells you we're dealing with the single element itself, sulfur. And it has a -3 charge, okay? No, that's not right. It's -2 charge because it's in group 6. Okay, zinc has a +2, so that's -3, -2, and a +2. That's the correct formula. Okay, so sulfide, the sulfide has one less oxygen. Okay, and the sulfate. So you see the naming there, how it could be confusing, the 8, the ite, and the IDE, ide. Hopefully you can see there how you can distinguish between those 3 choices there. Okay, I tell you what, let's do a quick, it's 2:11. Let's do a quick 10-minute break for a second, for a little bit. We'll come back and call it at 2:20, okay? Let me pause. Okay, guys, I'm back. All right, so with respect to variable charge metal ionic compounds, we touched on this before. We used the Roman numeral number to distinguish which metal we're working with. And then the non-metal remains the same, either as a polyatomic ion or as a single element anion with the IDE suffix. So this one here is, you're given CuCl2. Well, we need to first figure out what is the oxidation number of copper. Okay, and going back to the general equation I gave earlier, where the total number of cations equal to total number of anions equals 0, you use that equation here and set up a little simple algebraic equation here. So since we don't know what the charge is for the copper, we got Cu. So Cu charge oxidation number plus the oxidation number of the chlorides. We know that each one has a -1. Why do we know that? It's in group 7 and -1, and there's 2 of them. So we have a total of a -2 for the chlorides, the 2 chlorides. And so it's Cu minus -2 equals 0. We solve for copper, and copper must be A+2. Okay, that tells you that we need Roman numeral 2 to name this compound. So the name would be copper, Roman numeral 2, chloride. Okay, here we go again. We have lead and oxide. Okay. We don't know the charge for the oxidation number of lead, but we do know that each oxygen is a -2. That means that we have a total of a -4 for the oxygens. So that means that the lead must be A+. Oh. The lead must be equal to A+4, which infers that we're going to be using Roman numeral 4 to give its name, IV. Okay. You ever notice, speaking of Roman numerals, that there isn't really a Roman numeral for 0? I guess they didn't have the concept of 0 then. Anyway, IV represents, V is 5, I is 1, so you subtract 1 from 5, that gives you 4. That's hence IV. If it's 6, it's V, and then the I follows the V, and that gives you V plus 1, which is 6. All right, so the name here would be lead, Roman numeral 4, oxide. Okay, nickel and the bromide. Okay, nickel and lead and copper are not part of the 16, so we have to use Roman numerals. But to find out which oxidation state it is, we need to calculate and figure it out based on the formula that they're in. And so we have nickel here again. We don't know what it is charge-wise, but we know the sum of the charges, anions, is a -3. How do I know that? Because each bromide is a -1, okay? And we've got 3 of them. That infers that nickel must be equal to a +3 oxidation number, oxidation state, which means we're using Roman numeral +3. Okay, manganese sulfate. Okay, again, which one? We go at sulfur, we're thinking sulfide, but it's not. Why? Because right next to sulfur is an oxygen. So think polyatomic ion, go to the table, you'll see that SO4 is the sulfate and that it has a -2 charge, -2 charge. Then we run through that. And so we have Mn, okay, plus the -2 charge for the sulfate equals 0. So Mn is equal to a +2 oxidation state. Hence, we use Roman numeral 2 for in its name. Okay. Here we go with copper. Again, NO3. We think N, we think nitride, single element. I sound redundant, but I'm going through a systematic stepwise until you become familiar with it. Then you can go directly to whatever you need to go to stepwise. So we got nitrogen, thinking nitride, but however, we got oxygen right following the nitrogen, which tells you polyatomic ion. Go to the table, we find that NO3 is the nitrate ion, and it has a -1 charge. So we got copper plus a -1 is equal to 0. That means that copper here must be a +1. And so we're using Roman numeral I, or 1, for the name. So we got copper, Roman numeral 1, or I, nitrate. All right, CO, your first inclination would be carbon monoxide, but it's not, right? Because you got C, and then right following that is a lowercase o, which indicates cobalt. Cobalt's not part of the 16. Therefore, we need to use Roman numerals, and we need to figure out, okay, which one do we use? So we got cobalt plus the charge for the anion, which is nitrogen, ionic nitrogen, which now becomes nitride because there's nothing following nitrogen. It's the single element itself, okay? And it's in group 5, which tells us it has a -3 oxidation state. Therefore, this cobalt must be a +3, and therefore we're using Roman numeral 3 in parentheses for the name. So this would be cobalt, Roman numeral 3, nitride. Okay. There's a good example of the nitrate and the nitride right next to each other. Again, you can mix and match different combinations here. Add some more. You got the lead with the bromide, lead with the sulfate or the sulfite, lead with the nitrate or the nitrite, and lead with the nitride. Okay. And the same with the cobalt, go the other direction, cobalt. And, so you can see how you build up your database with cobalt with nitrate, cobalt with sulfate, cobalt with bromide, cobalt with oxide. Obviously, the numbers, the formulas would be slightly different, but you can figure those out. And so you're probably up to about 1,000 compounds, ballpark, okay, that you can put together. Mix and match here, so to speak. Oh, last one. Sorry about that. All right. First thing here you see is parentheses. I see a parentheses right there. That tells me, without even having to think about it any further, I got a polyatomic ion. So I look inside the parentheses, I got a CO3, go to the table. That turns out to be cobalt. Okay. It's cobalt. What am I thinking? Carbonate. I got cobalt in the brain from the previous one. And so then we have the carbonate, which has a -2 charge. Okay, so we set up the algebraic equation like normal. Okay, nothing's different. Other than that, we're going to add some additional things. First of all, we have 2 irons. Do we not see that subscript on that iron? That means it's 2Fe. Okay. Now the cobalt has a -2 each one individually. The parentheses, the outside parentheses tells us we have a total of 3. So we have a total charge of a -6 for the carbonates. The carbonates, the CO3s. Each one is a -2, and we got 3 of them, okay? And then so -2 times 3 is 6. And so we have our algebraic equation set up here. So we've got 2Fe equals 0. Let's solve for Fe. Let's add a 6 onto both sides of the equation. So we simplify the equation to 2Fe equals a +6. Okay. We want to isolate iron. And so we divide through by 2 to isolate the iron. So that means that each iron is a +3. Okay, is a +3. And so the name here would be iron, Roman numeral 3, carbonate. Now, you could do this algebraic equation like we just did to solve what the oxidation number is for iron. But look at this. The subscript of the anion, which is a 3 circled over here, ends up to be the charge for the iron, the cation. And isn't the subscript, let me change this color a little bit. Isn't the subscript of the cation, isn't that the oxidation number for the carbonate, -2? So I could at a glance just look at the subscript of the anion to tell me the charge of the cation, which is +3. Okay, the little extra tool you can use. But until you're comfortable with that, run it through an algebraic equation so you can figure it out. Figure out what the oxidation number is for each iron. Don't forget the 2. There's a 2 there. You may have a 3, a 4, whatever, but eventually you need to solve just for iron itself. Okay, so its name, as we calculated, would be iron 3 carbonate. Okay, and again, you can mix and match with the lead carbonate, nickel carbonate, manganese carbonate, copper carbonate, cobalt carbonate, iron. Obviously, you can even make iron 2 carbonate. Okay. And then all the other metals that we've been working with so far, group 1, group 2, and everything else. So you see, you're building up your database of the compounds that you can come up with the formula and the name. All right, in this case here, let's work through it real quick, okay? First things first. We have strontium and we have the hydroxide. So the hydroxide is a polyatomic ion. You look that up. SR is in group 2. So SR is a metal and it has a group 2, so it will have a +2 oxidation state, which means that I'm going to need a parentheses for the hydroxide because each one is a -1, and I need 2 of them to cancel out the +2 of the strontium. Okay. Next one, I'll give all the answers here in a bit. We got Au, which is gold. Okay, we don't know which one oxidation state this is because this gold is not part of the 16, so it's a variable oxidation state. So we got to calculate that, and so we know that gold is Au plus -3 for the chlorides because we know that each chloride is a -1 and there's 3 of them. And so in this case, gold will be equal to a +3 oxidation state. So there'll be a Roman numeral 3 in the name. Zinc, we know is one of the exact oxidation states, +2, and oxide has a -2. So we can simply put those together. Okay. We got PO4 -3, polyatomic ion, the phosphate. Barium is in group 2, and so we know that will give us a +3. And so now we have a -3 and a +2 to combine. So we look for a common number, which in this case will be 6 again. So we're going to need 3 bariums and 2 phosphates. That means we're going to need a parentheses around the phosphate. Okay, we'll come back. We'll show you the full formula in a bit. Here we have SO3. We might think sulfate, but verify that in the polyatomic ion table. The SO3 is the sulfate. It has a -2 charge. Okay, the lithium is in group 1. When it becomes ionic, it ends up with a +1 charge. That means that I'm going to need 2 of them to counter the -2 of the sulfite. Okay. Aluminum has a +3, it's a metal, group 3. Sulfur is in group 6. It becomes a -2 when it becomes an ion. And so now we have a dissimilar charge here. We need to find common ground, common number, which will be 6 again. So we're going to need 3 of the sulfides and 2 of the aluminum to give us a total of +6 and -6. Right. And then here they're asking you the last one to just name it. Well, obviously we got copper. Okay, Cu. And then we look at the parentheses, and so that's a good indication of polyatomic ion. So we go to the table, we look up NO3. Eventually we become familiar with the NO3 and don't have to go look it up and realize that this is nitrate. Each nitrate is a -1. So copper, and there's 2 nitrates, so we got a total of -2. And so we set up our algebraic equation, Cu plus a -2 is equal to 0. That tells you that copper must be a +2 oxidation state. So we're using Roman numeral 2 for that name. So it's copper, Roman numeral 2, nitrate. All right, let me clear the table here. So we end up with the following. A little bit neater. So there's strontium hydroxide. You might get used to this, that hydroxide, OH is a base. These are compounds that are called acid or bases. That's a base. Get used to recognizing that. We're going to use it quite a bit in the next chapter. Okay, gold Roman numeral 3 chloride, zinc oxide, barium phosphate, parentheses around the phosphate because we need 2 of them. Then a lithium sulfite, because that's the SO3, not the SO4, which will make it sulfate. Then aluminum sulfide, and then copper Roman numeral 2 nitrate. And again, as stated, you mix and match strontium with chloride, strontium with oxide, strontium with phosphide, strontium with sulfite or sulfate, strontium with sulfide, and so on and so forth. So you've again added some more compounds to your database. Okay. Now, if you haven't had a chance to take that nomenclature, by all means, that's what we've done with this chapter. Start taking it. You'll see you'll probably get a good close to 80% with what we just gave you right now. Okay, so go through it. Start doing it now and get practice. All right, write the formula is what they're asking you to do here. Well, if we're given a name, so we're going to write the formula. So number one, the first thing to do is first write everything into ions. Okay, because you need to know the charge of the ions before you can put them together. So the first one, we got sodium and nitrite. Nitrite. Now you might be tempted to put a nitrogen, but it's not nitride, IDE, it's ITE, which is the NO2, which is a -1, okay? And so here we can simply put it together as a 1-to-1 ratio. Okay, let me put these up here. So we got sodium and the nitrite. Okay, nickel 3 oxide. Well, break it into ions. Nickel 3, remember the Roman numeral belongs to the metal, so it's a +3. And we know that the oxide is a -2. Okay, so that means we've got 2 dissimilar charges again. So we can find a common grounds. That means we need 2 nickels and 3 oxides. Magnesium. Magnesium is a +2 group 2 element. So it has a +2 charge. Iodide is a group 7 element, becomes iodide. So it has a -1 charge. That means I'm going to need 2 of them to counter the +2 of magnesium. Aluminum, it's a group 3. We know that it's one of the constant oxidation number metals, and it's a +3. And cyanide, well, that should direct you to the polyatomic ion, the cyanide. You'll find CN- for that whole polyatomic ion. We need 3 of them to counter the +2 of aluminum. Okay. And so before we write the formulas, break it down to the ions, and then from the ions, it will tell you how much of each you need. And from that information, you can go on to write the formulas. Let me clear up my mess there. And you end up with the following. Okay. Na, sodium NaNO2, and then nickel, 2 nickels, subscript 2, oxide subscript 3. And MgI2, and then cyanide, since we need 3 of them, we need a parentheses around the cyanide, excuse me, to give us aluminum parentheses SCN and parentheses subscript 3. Okay. So this is, up to this point, this is what we've been dealing with respect to ionic compounds. Remember, no prefixes. We wouldn't say aluminum tricyanide, just simply aluminum cyanide. When we get to covalent compounds, which is made up of nothing but nonmetals, then we are dealing with prefixes, okay? Now, we don't deal with ions here because remember, these guys are covalently bonded. These are sharing electrons. So they don't have full charges like ionic compounds, but they have what are called oxidation numbers. And so that's why we use the term oxidation number, because it encompasses not only the ionic compounds, but the covalent compounds, okay? Now, the prefixes that we utilize are 1 for mono, 2 for di, 3 for tri, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, and occasionally you might see nana, N-O-N-A for 9, and octa, deca, D-E-C-A for 10. Okay, but we're using prefixes, and that tells us how many of those atoms that we utilize. Okay, so the generally the name is this. We have nonmetals. The first nonmetal that you see generally is the central atom. The only exception with that would be like water, H2O. By convention, people write H2 and then O. Okay, hydrogen is not the central atom, oxygen is. But other than that, all the ones we deal with, the central atom, nonmetal, is the central atom. Hence, its name remains the same. It's not going to be the IDE extension. So if sulfur is a central atom, then its name will be sulfur. If it's sulfur follows the central atom, then it becomes sulfide, okay, because it's bonded to the central atom. So it can be the central atom, or it could be bonded to the central atom. When it is not bonded and is a central atom, it's simply whatever name it is. And we may use a prefix if there's more than one, okay? So we got prefix and then plus the nonmetal name, first name. If there's only one first nonmetal, then we don't use mono. We just say the name, whatever it is. Hence, carbon dioxide. We don't say monocarbon. We just simply say carbon. If it's a element after the central atom by itself, then we add the prefix mono. Hence, carbon monoxide, right? Oxygen is an atom all by itself after the central atom. So we have to use the prefix mono. Okay, some more examples in a second and then in a bit. So we got the prefix and then the second non-metal name plus the IDE. So oxygen in the inorganic compounds or ionic compounds, we converted its name to oxide. We continue that practice here. So oxygen then will be oxide, hence carbon dioxide. Okay, not carbon dioxygen, carbon dioxide. Okay. Don't use the mono for the first non-metal if it's by itself. Carbon dioxide, you can see carbon is the first metal all by itself. We don't need to do mono in front of it. And then we have an oxygen, which is bonded to the central atom. So the name remains like we did with the ionic compounds, goes to oxide. And then we use the prefix di to designate that there are two oxides. Okay. Here we have same similar thing, except now we only have one oxygen. So when we have one oxygen, then we have to utilize the prefix mono. Okay, so it'd be carbon monoxide. Okay, here my suggestion is this: when you're given, you look at the formula, you see they're all nonmetals. Okay, break it down again. Another systematic approach here. Break it down to the parent name by looking at the atoms involved. Okay, so we got phosphorus is written first. So there's two of them. We'll come back to that in a second. That is the central atom. So we simply write phosphorus. Okay, and then oxygen's bonded to the phosphorus, and like we did with oxide, carbon dioxide, the name is oxide. Okay, so that is the parent name, if you will, the base name, phosphorus oxide. Now we come back and add the prefixes. So since there are two phosphorus, we add di. And since there are 5 oxides, we use term penta. Now, the English rules as far as sentences is this: when you combine a prefix that ends in a vowel with the prefix that begins with a vowel, you're supposed to drop the A. So technically, we drop the A in pentoxide. Okay. Now, if you forget to drop the A, I'm not going to count it wrong. Okay. So we end up with the name here, pentoxide. Here we forgot to drop the A. Either one, from my perspective, would be correct. Obviously, you're teaching English. If your English teacher saw this, I'm sure the teacher would get all minus 30 points. All right. All right. So let's do the next one. Similar situation. We have the phosphorus and we have a fluoride. Now, fluorine, okay, we maintain as if it was an ionic compound. The phosphorus is the central atom. Okay, so we continue with the name phosphorus. First thing I do is write the base name and okay, base name, and then I use tri. Oh, give me phosphorus trifluoride. Oh, I think I misspelled fluoride. No, I did. It's right. F-L-O-U-R-D. Yes, phosphorus trifluoride. So no first name, the phosphorus by itself. No mono. When it's by itself, just simply the name. Okay, here we have now iodine. I can be iodide, right? If it's bonded to something, it is called iodide. Here, iodine is a central atom. Okay. Let me write this down. So iodine is a central atom, so it remains its given name, element, iodine. Then bonded, right, immediately following the iodine are what we would think are the fluorines, but they are bonded to iodine. So those, as we did the previous one, are fluoride. Okay. And we go back, there's only one iodine, and we hit it with the prefix, so hepta. Okay. Now let me ask you a question here. That is the name. You see the formula. Can anyone calculate the oxidation number of iodine in number 4? What would it be? Now remember, it's not iodide. If it was iodide, then there would be a -1. Okay, but it's not. What would be the oxidation number we got here? Let's look at the answers. A -1? Not quite, because iodine is the central atom. And all of the fluorides, 7 of them are bonded to it. And use that general equation that gave you number of cations plus number of anions equals 0. In this case, 0. We know that the fluorides are -1, and there's 7 of them. What does that infer that iodine must be in order for that molecule to equal 0? Exactly, +7. Okay, you got it. When we talk oxidation number, you got to be specific, because 7 could be -7 or it could mean +7. In this case here, it would be a +7. That's correct. Okay. Yeah, unusual, but it does happen, these compounds. We give you the basic the basic oxidation number and tell you that only these guys can bond this way. We have, at general chemistry level, that's the case. But when you get upper level, we realize that no, these guys do bonding. Like we tell you that the noble gases are inert. And for Chem 130, that's correct. But we know also that the noble gases, the bigger ones, the krypton, radon, and so forth, they can react because those electrons are way out there. They're not affected very much with the nucleus. So they're out there to do things and act like a valence electron. Anyway, let me clear my table here. Almost done with this chapter. Okay, so given the formula, give the name and vice versa. Okay, so who would like to take this one? Here we got bromine's a central atom. Remember, as we write it, what's first is a central atom. Here we got 3 of them. Okay, this is quite a fancy complex actually, and then we got 8 oxygens around that. But let's name it. Who would like to name that compound? Systematic approach. Write the base name first, and then from there, add the prefixes. Tribromide. Yep. Octoxide. You got it. With or without the A will be okay. Okay. Here's with the A, but technically the A should be dropped because the A and the O are 2 vowels. All right, how about this one? Who wants this one? Phosphorus here. The base name is phosphorus and sulfide. Okay, phosphorus and sulfide. So what would you do to finish it up? Come on, what's the prefix for 4? Tetra, right? And the prefix for 7, hepta. So hence, the base name is phosphorus sulfide. Add the prefixes. You end up with tetraphosphorus heptasulfide. Okay. All right, here's this one. Base name, sulfur is the first element. That's the central element. And then we got the oxygen, which is second, so it'll be oxide. So the base name is sulfur oxide. What about the prefixes? Who wants to take that one? Sulfur trioxide. That would be correct. In fact, the next time you're in front of a car that's kind of gassy and got smoke coming out, and some of that smells like a rotten egg odor, that's what you're smelling. Unfortunately, that SO3, sulfur trioxide, gets up into the atmosphere, reacts with water, forms sulfuric acid, which is an acid. And then when next time it rains, it becomes an acid rain and affects our soil, raises the pH or lowers the pH of the soil, which then allows other heavy metals to be dissolved and get into our water system. Okay, now this time you're given the name. Now you're asked to give the formula. And so just reverse the process. When we're given the name, you give the base name. Here, give the base formula. Well, we got iodine and fluoride. So the base formula would simply be I. Yep. And what's my little marker here? A marker. All right. So the base formula here would be the I for iodine and the fluoride. Okay. So that's the base formula. Go back and do the prefixes, and you see there's only one iodine. So there's one iodine, and hexa is 6. So there's the formula. Okay. Next one. We give it a name, write the formula. Same process I just did. Find the base formula first. We got the chlorine and the oxide. And so it's ClO. That is the base formula. Then you come back. The prefixes are the suffix. So dichloride gives you 2 there. And penta gives you 5 there. Okay. And so the formula would be Cl2O5. Okay. Here, now we're back to the formula. So you write the base name again. So it's phosphorus and iodide. And then you go back and use the prefixes. And you end up with diphosphorus, because there's 2 phosphorus, and tetraiodide. There's a little bit of a tongue twister. Okay, so there's 4 of them. So that's the name. That again, technically, with the A dropped out, which would be a little bit of tongue twister. Tetraiodide. There you go. All right. So when it comes to covalent compounds, we use prefixes. Okay. If you're given the formula, then write the base name and then add the prefixes for how many of each atom you have. And if you're given the formula, the name, and you want the formula, then again, write the base formula and then throw in the prefixes as you need them. Until such time you can read it and automatically, write it out when I have to do that. All right. A few reminders. Prefixes are again only for covalent compounds. Okay. Roman numerals are only used for those metals, ionic compounds, that have a variable oxidation number. They're not part of the 16. If they are part of the 16, no Roman numerals. Okay. With respect to the polyatomic ions that are given in the table, we don't change the name. That is the name for that polyatomic ion. So nitrate is nitrate. We don't name it nitrogen, whatever, trioxide or anything like that. Just nitrate, nitrite, whatever the case may be. Okay. And with that, we try this one. What do we got here? BaCl2. What do you think the name is? Who would like to take a shot at that? No. Come on, BaCl2. I'm sure somebody got it. You can unmute yourself if you like. There's only 5 of us here. All right, first one, barium chloride. Christina, you got it. All right, okay. How about someone try the NO2? Okay, first of all, look at that. Recognize that it is a covalent compound. Nitrogen is the central atom, and then 2 oxygens bonded to that. What do we got? Nitrogen dioxide. That would be correct. Yeah. All right, a little bit more challenging one. Number 3 here. You got Fe3PO4 parentheses 2. Parentheses should tell you polyatomic ion. I go to my table to figure out what is the PO4, because obviously it's not phosphorus, right? Or it's not phosphide because they got oxygen there. So it's got to be phosphate. Okay. Then I look at the iron, Fe. It's not part of the 16. So that tells me that I need a Roman numeral. So I need to figure out what is the name, and it's iron and it's phosphate. Okay. That part I got figured out. Now the question is, it's not part of the 16. That is the metal. I need to figure out what the charge is. And so that would be iron 2 phosphate. Very good, Leah, you got it. Okay. Now, at a glance, I can see the phosphate, there's a subscript 2, so I can use that. There's my iron 2. Number 4, diiodine tetroxide. Okay. So base name iodine, an oxygen. Prefixes 2 iodines, 4 oxides. So I got I2O4. And then silver sulfate. Sulfate, the ATE should tell you, go to the polyatomic ion table. It is SO4 -2. Silver is part of the 16. It always has a +1. So therefore, I need 2 of them. So I would have Ag2SO4. Okay. And then finally, nickel 3 sulfide. Nickel 3 is that's the charge for nickel. That's the oxidation number you're using, which is a +3. The sulfide, we know that has a -2 each one. So I got a dissimilar charge here. I got a +3 and -2. Got to find a common number. And therefore I can go 2 and 3 sulfurs and 2 nickels. All right. There is a worksheet on the website. So that would help you out to get more practice. Okay, don't forget you also have the study mate to help you out. And do start taking some attempts on the nomenclature exams. Get some practice in there. You'll soon learn. You'll probably knock that out pretty quick. Okay. All right. So with that being said, congratulations, end of chapter 8. All right. Any questions, comments? Yeah. All right, because with that, I'm going to have to jump into chapter 9 real quick. All right, so this particular one deals with acids and bases. All right, now, earlier, I had stated that ionic compounds, which is a combination of metal and nonmetals, when we put them in water, they will separate. They will dissociate, hence ionize, create these ions. And I said at that time that only the ionic compounds, that occurs for the ionic compounds. Now, there's degrees of dissociation. Some of these ionic compounds dissociate 100%. Some do not. They dissociate maybe much less. It could be 5%, anything less, okay? But the fact is that they do dissociate. They're just degrees of dissociation. I stated also that covalent compounds, when we put them in water, do not dissociate. They remain intact. They don't form any ions. There is only one exception to that, and that is covalent compounds that are acids. For example, HCl is an acid, okay? It will dissociate. It's a covalent compound that does dissociate. So covalent acids are the only compounds that do dissociate to form ions. Now, what kind of ions they form? Well, they form very specific ions. Let me share with you something special about hydrogen. Okay, hydrogen hydrogen, as we know, has a 1 valence electron. So the Lewis dot structure for hydrogen is simply 1 dot in there for 1 valence electron. And the electron configuration is 1s1, 1 electron, okay, in the s orbital. Recall that the s orbital can handle a maximum of 2 electrons. And that's what can happen for hydrogen. It's so unique that it can pick up an extra hydrogen. When I'm saying hydrogen, pick up a electron and have 2 of them. Why? Because it has room in that orbital. The result is because as an extra electron, it has a net negative charge. And this guy has their own little special name. that we use in chemistry quite a bit, in organic chemistry, called the hydride. It's a very strong base, okay? But we're not going to talk a lot about that. Oh, misspelled. Hydride. Okay. Well, hydrogen atom, again, that's why we put it in group 1A, because it has one valence electron. And even though it's not a metal, it has the capability, like the metals, to lose that one electron. And when it does that, it loses that electron. So now it only has a proton. And that 1s1 orbital now is empty, okay? With a 0, no electron in there, just a proton, giving us a plus charge on the hydrogen. This has a very specific name. We call that a proton, okay? It's nothing more than the hydrogen atom that has lost its electron. This is what gives the acidity to chemicals. HCl, when it dissociates, hydrochloric acid is a covalent compound. When it dissociates, it will go into water and dissociate to give us proton, which is the acid part, plus the chloride. So it dissociates just like ionic compounds to form the ions, even though it's covalent compound. So the proton is what gives an acid, what is defined as an acid. So anything that produces a proton in solution is considered an acid. We'll have more about that in a second. The other aspect is that polyatomic ion that I've been talking about, we use quite a bit, is that hydroxide. That hydroxide is what anything that produces this hydroxide is considered the base. Okay, so Tums, calcium hydroxide, is a base. Sodium bicarb. Sodium bicarb is another base that eventually breaks down to give carbon dioxide and water, but is a base. Okay, and let me clear all this up. So that is the uniqueness of an acid, the hydrogen. Hydrogen produces any compound that produces a proton, okay, is an acid. They normally taste very sour. As we all know, vinegar, lemon juice, very sour tasting, okay? They're very corrosive. They will react with metal and it cause it to corrode, react. And if we needed to determine whether something's acidic, we have something called litmus paper. We have two types, red litmus paper and blue litmus paper. Red litmus paper will turn, blue litmus paper will turn red if it's an acid solution. All this the litmus paper does is tell you if it's an acid or a base. That's it. Doesn't tell you the degree of acidity, just it's an acid. Okay, as I mentioned, anything that produces hydroxide ions in water is classified as a base. Okay, now bases themselves, I wouldn't recommend tasting them. They're very bitter and kind of chalky out of water in solid form. If you get some on your hand, it feels slimy. A good example of this would be liquid plumber. Liquid plumber is a strong base. You get some on your finger feels slimy. You might think that's a chemical. It's not the chemical, it's actually your tissue being broken down. So be careful. In fact, a lot of makeups use some mild alkaline solutions. The idea of that, not makeups, but face treatment stuff has an alkaline solution, so it will base solution. So it will break the tissue down and get rid of dead tissue and so forth. So you're ripping up your skin, I guess. All right, the red litmus paper, if it's a base, will turn blue if you put it in a solution of a base. Now, first definition, called the Arrhenius definition, a definition of an acid or base. Arrhenius scientist lived a long time ago. He determined that any compound that produces a proton, which is right here, is by definition an Arrhenius acid. Okay, Arrhenius acid. Now, any compound that produces a base, hydroxide is a base. So here's a hydroxide, and there's sodium hydroxide here. Now, by and large, most of the compounds that produce hydroxide will be ionic compounds, okay? Now, here's something interesting about an acid and a base. If I had to take a guess, let me do this. If I were to combine a proton with a hydroxide, couldn't anybody tell me what you think the product would be? And think in terms of what you do if you ever taken Tums or milk of magnesia. That may help. What do you think? And you have H plus in your stomach, and you're taking Tums that contains OH. What do you think is happening? You're neutralizing it. Okay. The fact is that a proton plus a hydroxide will always 100% give you water. You have neutralized the acid and the base. Okay. All right. And that's basically what's it's telling you here. And this is one of the 6 types of reactions we'll be talking about, I believe, in the next chapter. And this is called neutralization reaction. So if I take an acid, in this case, hydrochloric acid, okay, and I react it with a base, I get water. So I got the H, the proton coming from the acid, the hydroxide coming from the base to give me water. See that? And the negative or the anion of the acid, which in this case is the chloride, and the cation of the base combine to give you sodium chloride, which is the base. Okay. Thank you. All right, aqueous system. Now we think salt. Okay, and all of us, we tend to think, and it's quite natural, sodium chloride, table salt. But with respect to chemistry, salt is any combination of a metal and a non-metal, specifically an ionic compound. So here, because we use sodium hydroxide, and in hydrochloric acid, we ended up with the salt, sodium chloride, but it could have been potassium hydroxide, and then we end up with potassium chloride, okay? And that's the salt or the ionic compounds, which are the cation of the base and the anion of the acid. Now, unfortunately, up to this time, we could not, Arrhenius definition did not only dealt with the hydroxide, okay? Well, there were cases, scenarios where there was no hydroxide involvement, but yet the acid was being neutralized. And so an additional definition had to be made. And hence we end up with the Bronsted-Lowry acid. Now, Arrhenius acid and the Bronsted-Lowry acid, basically the same thing, okay? In both cases, they produce or lose a proton. Either way, somebody's making a proton, okay, which is the acid part. Where they differ is the definition of the base. For Bronsted and Lowry, the base is whatever chemical accepts that proton, okay? Notice there's no hydroxide involved here, like the previous example. Hydroxide versus the proton gave you water. Here, what is happening is we're having a base like ammonia, which has, remember from the Lewis dot structure, it has lone pair of electrons on the nitrogen. Remember when we drew the Lewis dot structure for ammonia, we ended up with a lone pair on the nitrogen. I stated earlier that the proton has a missing s orbital. And so the proton can come in here and combine with that lone pair to form the ammonium. We went through this one too when we did the Lewis dot structure. Remember the ammonium ion. It's also one of the polyatomic ions. And so ammonia, NH3, with the lone pair of electrons, combine the proton to form the salt here, the ammonium salt, okay, with a plus charge on this thing, and then the corresponding chloride. And so it neutralized the acid, okay? Neutralized the acid with no hydroxide involvement. Simply the fact that it had a lone pair on there. You know, even the hydroxide can be thought as a Brownstein-Lowry, because if you look at the hydroxide, because you know you can do the Lewis dot structure, and you know what? The oxygen has 3 lone pair on there. And guess what? Here comes the hydrogen plus with an empty orbital, form a bond there and form water. And so even the hydroxide can be defined as a Brownstein-Lowry base because it accepted that the proton. But the Brownstein-Lowry base encompasses a variety of other chemicals that can be treated as bases without hydroxide being utilized as a base. Okay. So here's a space field model down at the bottom. And in this case here, ammonia, NH3, gains the proton. So FYI, ammonia, I think I'm sure you smelled ammonia pretty extensive. You can treat it with an acid to get rid of the odor of ammonia. Ammonia can be very powerful to form the salt. Salt's not going to be volatile. You're not going to smell it. And so if you have ammonia, you can treat it. You may not have hydrochloric acid at home, but you sure have vinegar. Okay. You can treat it with a little vinegar and that'll take care of it. So smelling vinegar. All right. Strong acids and bases. What do we mean by that? Simply put, a strong acid and a strong base totally dissociates 100%. Okay, that's it. If it's weak, it doesn't dissociate 100%. That's all there's to it. Okay. Now, we have given you here 3 examples of a strong acid. The first one's called hydrochloric acid. The second one's called nitric acid. And the third one is called sulfuric acid. When these chemicals go into water, they dissociate 100%. All totally dissociated into the ions, which makes them into classified as strong acids. Now, the question is, well, how do I recognize the fact that I have an acid? Well, by the formula as is given to you, 9 times out of 10, hydrogen will be written first. And first of all, notice that all of these are covalent compounds. There are no ionic compounds here, okay? And when it's written with covalent compounds with hydrogen first, 9 times out of 10, you're pretty much assured that these guys are acids. Second way to look at this is look at the counter ion, because we know the hydrogens end up with a proton, right? Look at the SO4. Doesn't that look familiar from the polyatomic ion? In fact, SO4 -2. And that's how we make the sulfate. We take sulfuric acid here, H2SO4, treated with a base. it reacts with the 2 hydrogens it has to end up with a negative charge, -2 charge on the SO4. Doesn't the NO3 look familiar? And doesn't the nitrate have a -1 charge? Yeah, because nitric acid treated with a base gives you nitrate ion. Okay, so hydrogen's norm is written first, then followed by whatever's followed by, okay, the NO3 or NO4, so on. All right, so dissociate, like I said, hydrochloric acid or sulfuric acid or so forth, they dissociate completely. So one way to show how the H2SO4 dissociates, let me draw it out. You can see we have H2SO4. So it dissociates, it has 2 protons, aqueous, plus the SO4 -2 ion, aqueous. Same is true for the nitric acid, HNO3. It dissociates with the H plus the NO3 negative nitrate ion. Okay. Now, the strong bases we're giving you by definition is potassium hydroxide and sodium hydroxide. We are going to learn that because these are potassium and sodium based on the solubility rules that also are on the periodic table, bottom right corner, because these are soluble in water, classified as soluble in water, they dissociate 100%. Dissociate 100% with the hydroxide means they are strong acids, okay? Because they dissociate completely 100%. Clear this up. Now, if I need to draw a diagram of a strong acid or strong base, I would depict it as follows. Here's a picture of a beaker of water with hydrochloric acid in there. Now, since hydrochloric acid is defined as a strong acid, that means that everything gets dissociated. So I would draw 3 or 4 pairs of the ions. Here I got 3 pairs. Got 3 chlorides and 3 protons. So I would draw it as follows, making sure that I have the respective charges on the ions themselves. Notice that none of these are still together, they're separated. Everything's separated, that means 100% dissociation, strong acid. I know it's an acid because it has protons in solution. On the right depicts a strong base. Again, 3 or 4 pairs of ions. Here we got 3. The sodium ion with the charges and the respective 3 hydroxide ions. Okay, that demonstrates, again, they're completely dissociated, they're not together. 100% dissociation, that depicts a strong acid. Excuse me, strong base. I know it's a strong base because of the hydroxide. All right, so to summarize the acids, we got HCl, hydrochloric acid, nitric acid, and sulfuric acid. 3 strong acids, and 2 strong bases would be sodium hydroxide and potassium hydroxide. Okay. Now, again, what do we mean by strong? It is they dissociate 100%, and they dissociate into their respective ions. Weak acids. Weak acids are those that do not dissociate 100%. They may dissociate 1 to 5%, regardless of the amount. It's a small amount, okay? That means that the bulk of this material is still intact and still put together. They have not broken apart. And we depict that in this equation here. You can see we have a double arrow. Okay, in the previous example is a one-way arrow, 100% dissociation. Here we have a double-sided arrow. Yes, this here is a general formula for, oh, let me introduce to the acids first. HF, hydrofluoric acid. If you do any etching of glass, you probably use this material. Okay, HF, a weak acid. Fluoride being highly electronegative, is just holding onto that proton very tightly, and hence doesn't let go. And the bond length is bond strength is very high. Hence the protons not eliminated as readily as hydrochloric acid. The next one is called carbonic acid. If you drink a lot of carbonated drinks, you're drinking some carbonic acid. Bubble some CO2 through some water. One of the products you make is carbonic acid. A lot of also found in soft drinks. The next one is the general formula. We haven't shown you the structure, but the general formula, notice that these guys all have a hydrogen written first. Again, that's indication we're dealing with an acid, okay? So the HC2H3O2, that is the general formula for something that you ingest if you like Italian dressing. That's vinegar. Okay, it's a formula for vinegar or acetic acid. And then again, the last one, phosphoric acid, also found in soda pop quite a bit. Notice, do you recognize the PO4? PO4, polyatomic ion, the phosphate, -3. And how you got a phosphate is you got the phosphoric acid has 3 protons. React with the base, you create PO4, phosphate. Carbonate, recognize the CO3. Okay, -2, that's the carbonate. Okay, -2 means they had 2 hydrogens to begin with, reacted with the base to form the carbonate. All right. So those are the weak acids, means that they do not dissociate 100%. Yes, there is some protons in solution. We can measure that, but it would be weak because there's not a lot of protons. The bulk of material is shifted to the left, hence a double arrow. So the bulk of the material is still intact together as in covalent compounds is, okay? And therefore, these are examples of weak acids. Now, how would I depict these? Okay, well, before I do that, a weak base. Now, here's an example of magnesium hydroxide, okay? That is also a weak base. And the reason it's a weak base, because we're going to find out about this, is in the solubility rules, magnesium hydroxide is classified as insoluble. What that means is the bulk of the material is still intact and in solid form in this case. Right here. Here's still in solid form. We do have a double arrow, just like the previous example, meaning that we do have some ions, but not a lot. And we do have some hydroxide in there, so that's why it's a weak base, because it is producing hydroxides, but not a lot. Now it's producing 2 hydroxides. Why? Because there's 2 hydroxides in magnesium hydroxide. Some people have a hard time with this, and it's understandable, but look at it this way. The magnesium hydroxide intact, think of it as a bicycle, okay? And the tires are the hydroxide. If I disconnect those 2 tires from the bicycle, okay, do I not have 2 tires or 2 hydroxides, and the magnesium represents the frame? Okay, so that's why there's 2 hydroxides. All right, now how do I depict these in a diagram? Well, in the left is HF. HF is a liquid. It's not a solid. Okay, so we will keep them together and intact. And so you see here that I have HF intact. I show at least one set of ions in solution, because even though it's insoluble, there is still some of it that goes into ionic form, dissociate, but very little. Magnesium hydroxide, which is a weak base, which again, this is an example of milk of magnesia. If you have some at home, take some out, put it in a clear glass, let it sit there for a while. You'll see it separate. You see a powder material at the bottom. That is the magnesium hydroxide. It's not very soluble in water, so it settles to the bottom. And then on top, you see your clear liquid. And we depict that by the bulk of the material still intact and is in solid form, down here in the bottom of the container. But since it's still weakly soluble, we still have to show some ions in solution. Don't forget the charges, respective charges, okay? So this is how we depict in diagram form a weak acid and a weak base. All right, so we have hydrofluoric acid, carbonic acid, phosphoric acid, and acetic acid. You know what's going to happen? We're definitely not going to be able to finish this chapter. So what I'm going to do is, since we're getting close to it, we're about halfway done. I'm going to extend the exam to the following week, because we need to finish this chapter first. And so that's what we'll do. Let me see what chapter we at. All right, so I'm going to stop it here. Slide 12.